All right, everybody, I thought I would go through how to solve question number 3 from your lateral displacement and angle of deviation assignment. There was a lot of confusion in class about it, so I wanted to make sure that I go through it, but I can't be at school tomorrow, so I thought this way you'd still get a chance to see how to do it and to work through these problems. So in this question, you were given a 30, 60, 90 triangle. And you had a light ray coming in as an incident ray and striking this boundary here. And in the diagram, it shows you that this travels straight through. And we know it's going to travel straight through because the angle of incidence at this boundary is 0 degrees. Basically, you have this light ray traveling along the normal. So when it hits this boundary, it doesn't actually refract. It doesn't change direction. It doesn't change, like it will change speed, but it doesn't change direction. And then this ray enters into this prism. Now, this prism, it tells you, has 2 different refractive indexes. The refractive index for red light is 1.49, and the refractive index for blue light is 1.51. And so this is because different wavelengths of light have different refractive indexes when they travel through a prism. And this ends up causing dispersion, where different wavelengths end up spreading out different amounts. And so you get those different colors coming out. And that's like the idea behind rainbows, or like how prisms split light. And that's the whole idea behind this question. This question is asking you, what is the angle of deviation for each of these 2 wavelengths of light? So to find your angle of deviation, one of the things that we need to do is extend our incident ray. So I'm going to extend my incident ray as a dashed line. And that dashed line is going to help me keep track of where this ray would have been traveling. I'm even going to label this my incident ray, because I want to keep track of that and not mix it up with the normal, because that's the next thing that we have to draw here, is we have to draw a normal. So 90 degrees to where this light strikes this boundary, there would be a normal. So I'm going to make another dashed line. And I'm going to extend this on both sides of this boundary. So there's our normal. Now, what this ends up doing is creating a bit of geometry for us to solve. So what we can actually do is figure out our angle of incidence just from this information. We actually don't even need a protractor to do this, which is handy because I do not have a protractor at my house. This is the angle of incidence. But one thing we know is that from the boundary to the normal, it has to be 90 degrees. So that's one thing that we know, is this has to be 90 degrees right here. The other thing we know is this angle was 30 degrees. And by this light ray cutting through, it's basically created kind of like a little mini triangle. And we can use this little mini triangle to help us solve things. This little mini triangle also has to be a similar triangle to the overall largest triangle, because they share a common angle, and this is basically just a smaller version of this big one. And what that means is that this right here, this angle is 90 degrees. So if this angle is 90 degrees, this angle is 30 degrees, the entire angle right there from my ray to here, this has to be 60 degrees. And that's because the sum of angles in a triangle have to add up to 180. So 90 plus 30 plus 120, or plus 60 gives us our 180 degrees. Now what that does is also help us understand what the angle of incidence is. Since the normal to the boundary is 90 degrees, this part of that angle is 60 degrees. The other portion of it has to add up to get to 90, which means the angle of incidence has to be 30 degrees. So this is the other piece of information that we know, is that our angle of incidence has to be 30 degrees. The angle of incidence is going to be the same for the red light and the blue light, because in the question they told us that white light was shining in. And white light is the combo of all the other wavelengths or all the other colors of light. So the light comes in, doesn't refract, but it hits at an angle of 30 degrees. Okay, so now what we want to do is we want to find our angle of refraction. So from here, we're going to do Snell's law, but we're actually going to do Snell's law twice. Once for the red light. And then we're going to do again, but we're going to do Snell's law for the blue light. Now, when we're doing Snell's law, N1 is actually for the prism because we're looking at how it's refracting out, which means that N1 for the red light is going to be 1.49. Angle of incidence is going to be 30 degrees. N2 is going to be 1.00 because it's traveling into air. And we are going to solve the angle of refraction. So you would use Snell's law, N1, sine theta 1, N2, sine theta 2. You'd work your way until you could solve theta 2. And I'm not going to do all of this work. I'm kind of trusting that at this point you can plug these numbers into Snell's law. And I believe you end up getting an angle of 48 degrees for the red light. You would do the same, and I guess maybe we should go back here. Let's think about what this actually means now. This 48 degrees, that's how the light would refract out. Now, like I said, I don't have a protractor, but I'm actually not going to need it to find my angle of deviation in the end. So from the normal, keep in mind, this is my normal right here. This light would refract at this angle. So my light is going to come out something about, that's probably about 48 degrees. Let's just go with it like that. Okay. So from here to there would be my angle of refraction of 48 degrees. But then I could find my angle of refraction for the blue light. And for the blue light, everything is going to be the same except for the refractive index. So angle of incidence, 30 degrees. Second medium is air. Solve for your angle of refraction. I am pretty sure by the time that you're done, you get a number somewhere around 49 degrees. So that means that the blue light should refract more, which is exactly what happens in real life. Blue light refracts more than red light, but our blue light is going to refract out something like this. And the angle from the normal to here is going to be 49 degrees. But this doesn't tell us our angle of deviation. The angle of deviation, remember, is how much it deviated from where the incident ray was actually traveling. And the incident ray was traveling right here, which means my angle of deviation is actually for the red light from here to here, and for the blue light from here to here. And if we think about how we can solve this, if I know how far it is from here to here, I could subtract that from the angles of refraction. And what that would do is then tell me the angles of deviation. Now, a little geometry allows us to know what this angle is. Because of the way these lines are set up, this angle and this angle, these two right here, are opposite angles. Opposite angles are congruent, and that means that this angle right here is actually 30 degrees. They are the same angle right there. So what that means is my angle of deviation for the red light has to be the angle it refracted, that total 48 degrees. And then we're going to subtract how far this angle was. And what we're going to be left with is just from here to here. That's what we're going to be left with when we do that. So 48 minus 30, we get an angle of deviation of 18 degrees. So that is our angle of deviation for red light. But we can do the same thing for the blue light, and it's the exact same process. The angle of deviation for the blue light has to be the angle that it refracted at. So from the normal all the way down to the ray, minus how much this angle was here, which was 30 degrees. And there we go. Our angle of deviation for the blue light was 19 degrees. So you can see, just with some basic geometry principles and with Snell's law, we can actually get ourselves to being able to solve what the angle of deviation is for both these wavelengths of light. Okay, so hopefully that helps you be able to solve question 3. And hopefully it helps you actually be able to solve some of these other questions where it's looking at a little bit more of a geometric view instead of doing all the measuring.